Hello, my name is Paddy Feeney, and today I'd like to explore with you some of the more interesting aspects of We're all familiar with the warmth and the comfort that flame provides, and we also know that if everything else fails, we can rely on it for light. And a very pleasant light it is too. Now, if we hadn't learnt how to control it, it could have destroyed us, because it can be dangerous. But we do know how to make it, how to control it, and how to extinguish it. And more than any other tool in man's command, it has been the means by which we have developed from our prehistoric, almost animal state to the intelligent, creative beings we all know ourselves to be. Without flame, there would have been no industrial revolution. And even today, it's an essential part of most modern technology. So, haven't we done well? Now, to get this far, man has had to design a whole range of burners. For instance, there's the Bunsen burner, which has fired many a discovery in science. And then these are Bray jets, also from the laboratory. The bar burner, and that's used a lot in cookers. And finally, two industrial burners. First of all, the Marshall burners, and then this one, which is the tunnel burner. Now, all of those are well-designed burners. On the other hand, this is the treacle tin burner. Now, what happens here is that the gas comes in through the bottom, and when it comes out of the top, it mixes with the air so it can burn. And the whole of the tin is full of pure gas, except for the fact that I happen to have cut off the gas supply. And so the flame will get smaller and smaller until... Now, what happened there was that as the flame used up the gas inside the tin, so you've got air coming in, and you've got a mixture of air and gas inside there. And when that mixture was exactly right to support combustion, the flame hopped inside the tin and triggered off the explosion. Pow! That, of course, doesn't happen with well-designed burners, but it does show the importance of having the right mixture of air and gas in the right place. But explosive mixtures do have their uses. An example of this is the internal combustion engine. It's powered by a rapid succession of explosions in each of the cylinders, and each of those explosions is nothing more than an intense flame of very short duration. But we've jumped ahead of ourselves a little bit there, because none of these burners could have been designed if we hadn't, first of all, understood the nature of flame, just exactly what flame is. Well, as you may know, flame is an intense chemical reaction accompanied by the production of heat and light. And to get that reaction, we need three things: a fuel, an oxidant, and some means of ignition. Now, nearly always, the reaction consists of the oxidation of either carbon or hydrogen. The oxidant usually is oxygen, which exists as just over 1/5 of the air that we breathe. So if we've got the fuel, the oxidant, and some means of ignition, we should, with any luck, get flame. Okay, let's concentrate for the next few moments on the fuels. Here's an example of carbon burning in air. And this is a hydrogen fuel flame. Now, if we cut off the oxidant or the fuel, the reaction stops, the flame goes out. In practice, of course, the fuels in common use are hydrocarbon compounds, combinations of hydrogen and carbon. Let's have a look at some. There's coal, which is very largely pure carbon with just a little hydrocarbon in it. And in fact, in this powdered form, coal is finding new uses. Now, that powdered coal is used a lot in big boilers in industry these days. Then there are the convenience fuels, which lend themselves more to automatic systems. First of all, the liquid ones, petrol for motor cars, paraffin for everything from the engines of jumbo jets to oil lamps, and of course, as we've already seen, solid paraffin for candles. The other convenience fuel is the family of gases, butane, propane, and methane, all of them hydrocarbon compounds. Okay, so far all the fuels that we've seen have been burning in a safe, controlled manner. It's when there's no control that things can go wrong. You see what I mean? But as long as we have the three ingredients in control, we can create safe flame. This is an example of methane burning in air, a common sight. But equally, we can burn air in an atmosphere of gas quite safely. The large glass cylinder is full of methane, and that small central jet is being supplied with air. It's clever, isn't it? But don't try this experiment yourself, because it is one of those ones that you have to leave to the expert. Right, at this point, let's look at another property of gases, and that is their density. Hot air balloons rise because the density of the air inside the balloon is lower than that of the cold air outside it. Other gases are lighter than air even without being heated. Hydrogen and helium, for instance. You just watch this. But what on earth is this man doing? Well, he might have discovered a leak in the bottle of propane gas he uses for cooking on board. Propane gas is heavier than air and would settle in the bottom of the cabin. A dangerous situation. As you can see from this bubble filled with propane. Natural gas, on the other hand, rises. Its main constituent is methane or CH4. Could I have a couple more, Dave? Thanks. It's also an odorless gas, so that smell has to be added to it before it's piped into homes. And just before we leave the subject of fuels, I should perhaps mention that combustion, of course, isn't restricted to the burning of carbon or hydrogen. Quite a lot of other materials also burn in the air. You're familiar with these, of course. Various metals and mineral salts are added to the firework filling to produce different effects, from bright sparkling flame to the brilliant varied colors. Let me just show you some. Here is a ribbon of magnesium. This is aluminium powder and powdered zinc. And you'll notice it comes out a kind of greeny color. Many metals produce a colored flame, and this is a technique used widely in laboratories to determine the presence of metals in all kinds of substances. It's called flame spectrometry. Here are some more examples. Cesium, lithium, potassium, rubidium, barium, copper, strontium. Right, now let's return to the more conventional type of flame to have a look at yet another of its properties. If we could have a few of the lights out, please. Okay, now watch this. Flame has the ability to travel. It has speed. And each fuel has its own flame speed. These two tubes are being filled with a mixture of gas and air. In the bottom tube, you've got natural gas, and in the top one, you've got town gas. That's the kind we used before the discoveries of natural gas around Britain. Watch what happens when they're both ignited at the same time. The flame speed of the town gas is much faster than that of the natural gas. Just watch it again. Now that is simply a demonstration of the fact that flame has speed. Obviously, if we wanted to boil a kettle, we can't chase it all over the countryside. So what we have to do is we have to anchor it down somewhere where we can use its heat. So we designed a burner and pumped the gas or a mixture of gas and air to it. But flame speed is important in the design of the burner, so let me show you how we measure flame speed. Here is an anchored flame. It has an inner cone and an outer mantle. It's the inner cone or reaction zone that we're concerned with when we're measuring flame speed. Using this model of a flame, we can disregard the mantle because what we want to discover is the area of that reaction zone. Next, we take the flow rate of the gas and air mixture going to the burner. We divide it by the cone, and we have flame speed. We've just demonstrated that a flame has got two parts to it. And in fact, we can separate those two parts. The method that we use was devised in 1892 by a man called Smithles, who was one of the first people ever really to study flame. The cone is anchored to the mouth of the inner tube. When we raise the outer tube, the mantle goes with it. Just to show that it's really there. You've separated the mantle and the cone. This was the earliest technique that helped us to study the products of combustion. And that's terribly important because it's only by studying those products that we can find out whether the flame reaction has been really efficient. Okay, let's assume for a moment that all we want from a fuel is heat. Now, if we could achieve perfect combustion, we'd only get two products from the reaction: carbon dioxide, or CO2, and water vapor. And you can see traces of each of those gases in these tubes. This one has crystals that detect the presence of the CO2. And this one, water. But although perfection is what we're after, it can be difficult to achieve it, and we may end up with other gases, some of them poisonous. For example, the deadly carbon monoxide, which is detected by the crystals in this tube down here, and which occurs when too little air is fed into the flame. And finally, with even less air, we get soot. Well, we've looked at flame itself and also what it produces. Now let's see how we can keep it where we want it to be. And this is where flame speed that we were talking about becomes important, because unless we take account of that when we're designing a burner, we can get a situation like this. Now this is known as a lifted flame, and what we want to do, of course, is we want to anchor that flame to the burner port so that it becomes stabilized. We can do this in a number of ways. For instance, if we put a glass cup over the burner, immediately the flame becomes stable. But why? Well, in the lifted flame condition, cold air is drawn into the base of the flame, and that keeps cooling down the reaction zone. If I put on the glass cup, the cold air can't get in, and instead hot gases within that cup are recirculated, and they keep reigniting the flame. This is called stabilization by hot gas recirculation, and it's used a lot in industry. Now, we can also get those hot gases to recirculate just by putting a metal bar in the flame. That's known as bluff body stabilization, and they use that a lot in rockets that are propelled by liquid fuels. But probably the most common form of stabilization, and the kind that I'm sure that you've got in your own gas oven at home, is to provide a source of ignition, a constant one, at the point where we want the flame to be anchored. And this is called pilot flame stabilization. Right, now we've anchored the flame where we can use its heat. And finally, I'd like to demonstrate the two main ways that we do this, by convection and by radiation. If we get a nice stable flame again, and then we put a strip of metal into that flame, after a while, you'll notice that the edges of the metal start to glow. And that is because heat from the rising gases is brushing off onto it. That is heating by convection. But we can make it even more efficient by increasing the velocity of the gases, as we do in the tunnel burner. Convection at its most powerful. But flame also radiates heat, just as it radiates light. We can increase its radiation by giving it a well-designed surround of refractory material, as in this modern gas fire. Now, we've taken out the middle of that fire so that we can show you the difference in the heat that it's giving out, and we measure that difference on this machine. So I'll just swing it across the fire. Right, now it's pointing at the refractory, radiant bit of it. That's the bit we took out. And now it's back on the radiant. I'll do that once more so that you can see it on the meter. Radiant, non-radiant, radiant. And that shows you how we can increase radiated heat. Well, there you have it, the basic flame. I do hope that you discovered some new facts about it from this demonstration. Of course, there are hundreds of ways in which we use it and control it in our homes, in our factories, and in our laboratories to the benefit of us all. So I'll leave you with just a few more examples. Goodbye for now. This is a craft which hasn't changed for hundreds of years. The smithy employs heat to soften the metal, which he can then beat into the required shape. Were it not for that electric fan fitted to the hearth, it would be almost possible to forget that the Industrial Revolution had ever happened. The Industrial Revolution, however, was dependent upon something else, something much more fundamental. It had at its root the fact that man developed the means for creating and utilizing flame in such a way as to be able to use the energy from it some distance away from the site of the flame itself. Flame produced steam. Steam powered the drive systems from which a number of machines could draw the power they needed to operate. Most modern factories power their machines with electric motors, but that simply illustrates the next stage of the development. The flame is now even further removed. It's back at the electricity generating station, miles away.
But flame is still at the root of all our industrial activity, providing power and, of course, the heat required in many specialized processes.
Most of our present-day applications employ flames that are locked away in furnaces so that we can extract the maximum heat. And our purpose today is to examine a number of the modern methods by which we can create and control that flame. Methods that are based upon two fundamental requirements, safety and efficiency. But before we examine these in detail, let's look at some of the basic facts about flame which we must consider in designing systems for its creation and its use. To create flame, we need these three ingredients: fuel, oxidant, and a source of ignition. For the moment, we will ignore the source of ignition and concentrate on the other two, because different fuels mixed with different oxidants burn at different rates. We call this flame speed. And to illustrate it, we will use two gaseous fuels. So the top tube we're going to fill with air and manufactured town gas. The bottom tube, air once again, this time, though, with the new natural gas that we've discovered around Britain's shores. And when they're ignited simultaneously, you'll see the result. The manufactured gas burns faster. The flame speed of any given fuel and oxidant imposes certain design requirements upon the burner. This, for example, is a single port burner. It's got the correct mixture of air and gas, and as you can see, a nice stable flame. But if I increase the flow rate beyond the capability of that burner, you watch what happens. The mixture was still right, but that burner was not designed to cope with that flow rate. One way of overcoming this is to provide a source of ignition at the burner port. It's also important to consider how and when we add the oxidant to the fuel. Here is an example where we supply neat gas to the burner port where it mixes with air. It's not a very efficient way of making flame, and therefore it is rarely used. A second method of mixing the fuel and the oxidant is with a partially aerated burner, so called because a portion of the air needed to sustain combustion is mixed with the gas before it's delivered to the burner port, entering through this shutter here. It collects the rest from the air surrounding the flame. And finally, we have a burner where all the air for efficient combustion is mixed with the gas before it is delivered to the burner. This is one of a family of burners called tunnel burners, and they offer a variety of applications because with this complete premix of the gas and the air, you can get a very, very wide range of flame intensities. This pottery kiln employs dozens of tunnel burners under automatic control to ensure the high temperatures required. Fully pre-mixed burners offer a highly efficient flame, one that can be used in otherwise impossible locations.
Here is an example of flame burning in a bubble of its own creation, totally cut off from the air. You can see from this how they carry out those welding operations underwater. But it has other industrial applications as well, for heating liquids. This is surprisingly efficient, as virtually the total heat generated is transferred to the surrounding liquid. In this example, it's heating an acid bath used for cleaning oxides off metal rods. Let's now return to the partially aerated burner to illustrate another aspect of flame which we have to consider, and that is the necessity to anchor the flame to the burner port. Now, a few moments ago we saw that if I increase the flow of air and fuel, the flame will simply blow away. And to hold that flame at the port, we added a source of ignition in the form of a pilot flame. Another technique that we can use, though, to anchor that flame is to install a cup shape around the burner port. This causes the hot gases within the flame to recirculate back to the base, and they act, again, like a pilot flame. Now, here is an industrial burner that works on that principle. A third method for stabilizing flame is to put a number of flames close to each other. There's a wide range of burners of this type, known as bar burners. Right, now we have shown that to create flame we need a fuel and an oxidant. And in this demonstration we also saw that different fuels mixed correctly with an oxidant have different flame speeds. In this case, both gases were mixed with air and the flame fronts moved quite slowly. We can also demonstrate that a different oxidant will have a dramatic effect on flame speed as well. For reasons of safety, we now have to use this metal tube into which we inject that same manufactured gas, this time mixed with pure oxygen. The source of ignition is here. Right, let's try it. That flame front moved at around 3,000 meters a second, so fast as to amount to an explosion. Now, that very high flame speed and the complete combustion of the mixture combined to produce within this tube a pressure 6 or 7 times greater than it was due to that rapid expansion of the gases. So, if we started with a pressure of 1 atmosphere, that's 100 kilonewtons per square meter, we ended up with around 700 kilonewtons per square meter, which can be quite dangerous in the wrong circumstances. We do, though, use these very fast flame fronts or explosions in a controlled manner every day. The internal combustion engine converts the high energy of these explosions into motive power by using the pressure to drive pistons, which in turn rotate a crankshaft. The illustrations that we've used so far have, I hope, suggested the enormous variety of ways in which we employ flame, whether they're locked away in furnaces or serving as hand tools in a process. We generally count upon flame to be instantly available and yet at the same time safe to use. So now let's deal specifically with the safe ways of creating and controlling flame. And first of all, I'm going to do something that we've all of us done many, many times, simply light a burner. There we are. Now that seems to be burning correctly, but I wonder if you could identify the 4 important stages I went through in order to establish that flame. I'll do it again. First, we need a source of ignition, correctly placed. Next, we turn on the fuel supply, that is, throughput control. Thirdly, I look at the flame to make sure that it's established. That's flame detection. And the 4th stage is to adjust the gas-air mixture.
a process that we refer to as proportioning. Now, that order is of fundamental importance whether the system is manual or automatic. It is the only safe way to light a burner. We can illustrate this quite clearly using the tunnel burner that you saw earlier. In this case, the proportioning of the gas and air is controlled automatically by the burner, which eliminates that final stage. We apply the ignition source as a repeating spark and open up the throughput control. A visual check to make sure that the flame is there, and then we increase the mixture flow to give us the desired intensity of flame. With premix burners, the mixing of the gas and air is frequently carried out automatically by the burner itself. So we therefore have just two factors left to consider in designing such systems: the methods for carrying out ignition and detection. Ignition can be obtained in several ways. The simplest one is to use a small pilot flame burning continuously, as we demonstrated earlier on. This method is used extensively in domestic central heating boilers and water heaters. We can combine the pilot flame with a flash tube. Though this method isn't much used nowadays, a portion of the air-gas mixture is fed into the tube from the burner. When it's full, the pilot flame ignites the gas in the tube and the flame shoots back to light the main burner. As I say, that method has been superseded by more efficient and economic forms of ignition. For instance, the spark igniter, which you'll find on most modern cookers. A single spark created by the application of pressure to a piezoelectric crystal is enough to light a burner. A glowing hot wire is another modern method of lighting burners, as with this domestic gas fire. You may have seen both of these systems, the spark and the hot wire, in battery-operated portable igniters like these. Right, that leaves us then just with flame detection, which is probably the most important consideration of all when you're designing systems that are going to work automatically. For reasons of safety, we program those systems so that if the flame is not detected at the appropriate stage of the process, then the fuel supply is automatically cut off. Obviously, this is a must in burners where the flame is out of sight. Where a burner is frequently being switched on and off, the simplest guarantee of safety is to ensure that the pilot flame is alight before turning on the main fuel supply. So we control that supply by first detecting the heat of the pilot flame. This loop of metal in the pilot flame is the detector in the form of a bimetallic strip. It's made of two pieces of different metal permanently bonded together. On this side, it's steel, on this one, brass. The amount that each of these metals will expand when heated is different, and indeed that's the basis on which they're selected. On a larger scale, I can show you what happens when heat is applied. This ability to alter its shape is employed to open a mechanical valve, permitting the main burner to light up when called upon to do so. Another method of detection, again using two different metals, is called a thermocouple. And as you might guess from that name, it also senses the heat from the flame. In this case, the two metals are welded together. And if we heat up that junction, we actually get a voltage generated across it. If we make a circuit with the other two ends of these wires through this meter, you'll be able to see the current flowing when I put the thermocouple into the flame. And of course, if I take it out, cools down, current decreases. To give you some idea of just how much power a heated thermocouple can generate, we've got one here that's connected up to an electromagnet which is holding up a 1 kilogram weight. And to show that it is just the heat that is holding it, I'll turn it off. There you are, you see. And now, here's a working example.
This main gas valve can only remain open if the thermocouple is being heated by the pilot flame. Cut off that heat, and the moment that the couple cools, the valve closes.
The illustration you've just seen senses the heat from the pilot flame to control the throughput of fuel to the main burner. Clearly, if we don't have a pilot flame, we would have to detect the flame from the main burner itself. In these cases, we employ some of the other properties of flame to design a detector. Now, you just keep an eye on that dial there while I go up to the other end of the room and ignite a small flame. Right, we should be getting a reading now.
And we're using this particular meter to indicate current flow, not the voltage.
Now, what we're detecting here is part of the energy generated within that flame and emitted as radiation. Our eyes are seeing the energy that falls within the visible part of the spectrum, but flames also give off energy in the infrared and ultraviolet ranges. We have detectors for each of these parts of the spectrum, each of them used for their own special characteristics. For example, the light-sensitive detector will react to flame and also to any other visible light. So really that's only useful in detecting very luminous flames when there's no other light source around to confuse it. Infrared is generated by flame and by anything else which radiates heat. By setting this instrument up so that it only responds to a flickering source of infrared, it becomes a flame detector. For flame control systems, though, we tend to rely mostly on ultraviolet detectors which react to flame but not to light. The lamp in this housing generates a high level of ultraviolet which can pass through the filter at the front of the box, and you can see how that detector is responding to it. I'll just screen that away for the moment because there's something else I want to show you, and that is the fact that sparks also emit ultraviolet. We can illustrate how we build this method of detection into an automatic programmer with this small package burner here. The detector is slotted into the back of it. Now, because this is usually built into a furnace, the sequence starts with a purge of air to make sure that there's no residual gas left in the combustion chamber, another safety factor.
The detector then senses that the spark is on and supplies fuel at the lighting up rate. The spark goes off, but if the detector sees a low-level flame is established, it then allows the main supply to be turned on. It then senses that the main flame is established and continues to provide fuel. But if I remove the detector to where it can't see the flame, that's what happens.
In automatic programmers like this, we use the detectors to guarantee that it's safe to supply the fuel at each of the stages. By the same token, these detectors can be used to sense the presence of flame where it is not wanted, to guard property against the risk of fire. There's one remaining property of flame which can be used to detect its presence and which I can show you using this meter once again. We make a circuit by connecting the meter to a battery and then connecting the battery in turn to the metal on the base of the burner. The second lead from the meter we connect to a probe. If we put the probe into the flame, you'll see what happens. The current flows. In other words, the flame is actually conducting electricity. Now, what's happening here is that within the flame, a number of the atoms have become ionized. At any given time, we have a portion of those atoms that have become positively charged ions, and, of course, a corresponding number of negatively charged electrons. If we apply an electrical potential difference using the burner itself and also the probe as the electrodes, then the current will flow through the flame just as it would through a conducting liquid or solid. Well, you have seen how we can ignite and detect flame, and also that we can proportion the gas and air and control the flow rate to the burner. We've also established that there is a correct procedure that must be followed to create safe flame. It's a comparatively simple one, but if we follow it, then that keeps us in control. And let me just remind you once again how important it is that we retain control.
Here we do not have control, and the cost of this one event alone ran into many hundreds of thousands of pounds. By contrast, the press of a button will initiate the process by which we can start automatic control systems out of sight and in complete safety. And here's an example of the kind of energy flame can produce for us when we have it in control. I hope that you've enjoyed these demonstrations.